Today we are looking at 15.4, which is called Is Momentum Lost? So when an object slows down, momentum appears to be lost, but where does it go? So the energy of movement is changed to other kinds of energy. So for example, friction in the brakes and the friction between the tires and the road causes heat. In some crashes, that is sometimes enough heat to even ignite the vehicle. Energy will also be lost in crumpling metal and shattering glass. In many collisions, momentum is not all lost. Objects that collide will continue to move in some direction. The amount of momentum that is lost will vary with the conditions and the circumstances. So, conservation of momentum. So this scenario here, a vehicle behind rear-ending the vehicle in front. What happens to the momentum of each vehicle? So what happens is the momentum of the vehicle in front will increase as it's pushed forward. It's going to experience a positive force. The momentum of the vehicle behind will decrease as the vehicle slows down because of that impact. So that vehicle will experience a negative force. Under ideal conditions, where friction is minimal and the vehicles lock together, the total momentum between the two vehicles does not change. This is also true if one vehicle bumps into another and there's no damage. So what we see here is that one vehicle will lose momentum at the same rate that the other vehicle gains momentum. So that is the law of conservation of momentum, which states that the total momentum of colliding objects stays the same after the collision. So here we're looking at before a collision, we have car A and car B, and then after the collision. So this car, the red one, is going to rear end the blue one. So it's happening on an icy road, so therefore there's minimal friction and it locks the vehicles together. So imagine the momentum of each vehicle before and after the collision. So before the collision, cars A and B, they're traveling at about the same velocity along the highway, and they therefore had close to the same momentum. After the collision, the momentum of car A has decreased, so shown by A minus X, because the hitting the car B caused a negative impulse, and that's why it's shown as the minus X here. The momentum of car B has increased. Being hit by car A causes a positive impulse, and that is shown by that positive X in this equation. Okay, so what to notice here is that the momentum of one vehicle decreased by the same amount that the momentum of the other vehicle increased. That's a negative X and a positive X. Head-on collisions are different. How does the law of conservation of momentum apply to head-on collisions? So this is when two vehicles are traveling along a highway in opposite directions. They have a head-on collision, all right? So it's different from a rear end. So scenario, two vehicles are traveling along a highway in opposite directions. They have the same momentum. They hit head-on. What happens? So both objects are in motion. They have the same momentum. The motion is in the opposite direction, so the forces would cancel each other out. Their total momentum would be 0, and so would their velocity. So they would stop completely. There would be a lot of crumpling. There'd be a lot of injury to the people inside. If one vehicle had greater momentum than the other, that vehicle would add momentum to the other vehicle, which would then move it backward. All right, so for example here, car A and car B, they have the same mass, 2,000 kilograms. They were traveling at the same speed, 100 kilometers per second or 28 meters per second. All right, so they have the same mass, they have the same velocity. As a result, they have the same momentum. Notice car A, it has a positive sign in front of it, just because it was moving to the right and car B is moving to the left, so therefore that's why it had a negative sign. It's just used to indicate that it was opposite momentum. So when the two cars collide, the value of their momentums will cancel each other out. So negative 200,000 and positive 200,000 equals 0. So they will stop. Hitting another vehicle head on, it's like hitting a brick wall at the combined velocities of the two vehicles. Although the momentums cancel each other out, the force is enough to kill the passengers. So calculating final momentum. So here, same diagram we had looked at before. So two cars with the same mass are traveling at different velocities. Car A is traveling at 100 kilometers per hour to the right, but car B is traveling slower. Car B is traveling at 60 kilometers per hour to the left. All right, but their masses are the same. Car A has a momentum of 200,000 kilometers per hour, and car B has a momentum of 120,000 kilometers per hour. It's just shown as a negative because it's traveling in the left direction. All right, so we know the momentum of car A and car B. We're trying to figure out the total momentum. So we're going to add the two momentum figures together. So 200,000 plus the negative 120,000, that gives me 80,000 kilometers per hour. All right, so therefore, both cars will move to the right. Keep in mind, the bodies inside the car will continue to move with their original velocities and directions unless they're restrained by seat belts or other safety devices. All right, so the Math Connect, there's one question to work on final momentum. 15.4, check your understanding, and then the chapter 15 review questions.